Hi everyone, welcome to this lecture. What I'm going to do is introduce electromagnetic waves and talk about light. So ultimately we want to know how light works, and the first part of understanding light is to figure out what it is and how it's created. And I think, as the name might suggest, it comes from electricity and magnetism. So in this video what I want to do is talk about how light is created, so obviously talking about what we see. I'm going to talk about the electromagnetic spectrum. I think a lot of you have experience with this, so I won't go too much in detail with it. I'll talk a brief amount about color theory. We'll talk about the speed of light in the wave equation, and then, of course, at the end of this lecture, we're going to talk about what can light do. And then I'll let the following lectures, in class, talk about what light actually does in more details, but I'll definitely introduce that today. So first of all, let's talk a little bit about what we learned so far in electricity and magnetism. So we know that a stationary charge generates electric fields, so that was one of our first lectures. So that charge will just sit there in space and make an electric field. And then we saw that moving charges can actually generate magnetic fields. So again, all based on the charge. We also saw that changing the magnetic field, I put that, but technically it's flux, but you get the idea, can actually make moving charges, or current. So changing the magnetic field can move charges. So, turns out the opposite's true. If you change the charge, or move it, you can make a magnetic field. So there is a relationship between electricity and magnetism. In fact, James Clerk Maxwell noticed that actually, even though we've been treating these things as separate things, they're actually one and the same. And he spent a lot of time unifying these equations and called them Maxwell's equations. So we're not going to cover these equations in class, but I think as a physics major, I feel obligated to at least show you that everything you learned up to this point can be summarized in 4 equations. Of course, this is using vector calculus, because as you might imagine, electric fields, and here's E for electric field and magnetic fields, are vector-based. And these basically summarize the effect of current and magnetism as we know it. So I'm not going to go through this, but every person should at least look at Maxwell's equations, because he took everything you learned and put it into 4 equations. It's kind of amazing. But I also show you this because he actually came up with something incredible from this, but he didn't even know it at the time. So down here, I don't know if you recognize these. I think you recognize this from magnetism. So if you remember, this is a magnetism permissibility of free space. So how well the magnetic field, goes through space. That's kind of what this is. The epsilon right here is the same thing, but for electricity. And it turns out that these two right here actually generate the constant for the speed of light, which is just mind-blowing. So he actually discovered light before he really knew what it was. So it was a pretty amazing discovery that he meant there, and it has to do with these 2 constants. But anyway, I know I did that kind of vaguely, which is fine. You don't need to, I'm not going to test you on that. But I'm going to talk about how light is created. And in fact, it's just made by a changing electric field and magnetic field. So all light is you take a charge and you wiggle it. That is basically what it is. Or accelerate it. It doesn't have to be a wiggle. It just has to be a changing motion. So remember, by physics 110, changing motion is an acceleration. So going from start and then accelerating, getting faster or slowing down. Or this is an acceleration because you have to stop and change direction. So I have that here as an oscillating charge. But remember, as this charge oscillates, it makes a magnetic field. And then as it's moving, because it's moving, will make, it makes an electric field. And then because it's moving, it also makes a magnetic field. Now remember that with the right-hand rule, the moving charge is always perpendicular to the magnetic field. So notice that B is perpendicular to E, and this is always true. In fact, I think the best way to do this is to show you this demonstration. You know how much I love these demonstrations. Go to physics, light. Take a quick break. Okay. Alright, so what you're seeing right now is a charge, and as you know, charges will give off an electric field. So that's what you see right here with these lines, giving off the electric field. So, let's go ahead and move this. So there we go, there's a charge moving right now like this. So notice that a constant charge, like this one, moving like this, does not make those waves that we see. But watch this. Let's accelerate that charge. So I'm now going to create a wiggle. Now you see the waves that are created with that, because we've changed the magnetic field. Well, actually, once again, we're looking at the electric field here. But notice that if I start to oscillate it, the electric field will generate these waves, so you can see them going out, just like that. And in fact, if I go in a circle too, I make waves. And then of course the bump, just like that. So let's go back to this one. Now remember, amplitude is more energy, so you make more pronounced waves. And then remember, frequency, we'll just see more bumps. There you go. Just like that. Trippy, huh? Okay, so let's calm down here. And I hope you get the idea that an oscillating charge makes these waves, because we're changing the the electric field like that. So I'm going to stop that charge. And then notice that a stationary charge doesn't make waves, and that a constant charge does not make waves. It has to be an oscillating or an accelerating charge. Okay. So here is another just cleaner view of that. So the pink is the electric field and the blue is the magnetic field. And they always make perpendicular, so they oscillate, if you notice, kind of perpendicular to one another, up and down like that. But notice that the direction of the wave is, of course, this is three-dimensional, is outward. So this is a transverse wave by definition because the disturbance is perpendicular from the wave travel. Now, I said the transverse part. Now, no medium necessary. That's a really important feature of electromagnetic waves. Allows it to travel in space or in places of vacuum. But notice the thing that's creating the wave is the electron. In other words, where we had sound, in order to create the wave for sound, we had to push particles. So, there must exist particles to push. Hence, we need a medium. But when it comes to electromagnetic waves, like I said, it has to do with the oscillation of charge. That is the medium, although that's not necessarily true. It's how the wave is formed. So you don't need particles to push because it's not based on pushing particles. So what happens is the amount you wiggle the wave defines what we call it. So very slow wiggles are radio waves. So actually, let me take a quick step back. Turns out that when people were studying the electromagnetic, waves, they wanted to kind of like group together the frequencies so they can talk about it since it's a spectrum. Now, a spectrum means that there's no defining endpoint to some of these, areas. So, if we do a slow wiggle, we decided to call that a radio wave. And in fact, there's no official cutoff where the radio wave happens. It's just like a grouping. So there's some like gray area right here. But that's what all these names represent, is just how much they wiggle. So slow wiggles are radio waves. If we go a little faster, that's our microwaves. And then if we go a little faster, and that's our infrared. And then turns out that visible light, what we call light, is actually this tiny, tiny, tiny piece of the spectrum. So that's visible. Now we call it visible for, I think, obvious reasons. It's what we actually see. Then we have the ultraviolet range. So that's the black lights that you might imagine. And notice that the wiggles get more rapid. And then the X-rays, and then the gamma rays. So we're going, as you see in the spectrum, from radio to gamma, we're increasing frequency. So the fastest oscillating wave is a gamma ray. And then the slowest oscillating wave is the radio waves. And remember frequency. I'm not talking about how fast it's going, just how much it's wiggling, so frequency. And again, we call it spectrum because there's no really set definition, but we say that this amount, this area is our infrared area kind of idea. So I said all this in the previous slide. I'm going to actually just mention energy right now, but talk about it actually in a few lectures later because it has to do with another effect. But just know that this is actually true. The energy does increase over time. So, strangely enough, how colors work is actually different frequencies of the same moving charge. So, slow-moving charges in the visible spectrum will appear to us as red. Medium is green, and then fast is that purple and bluish color. So again, this is all related to the oscillating charge. Now, if you notice, everything else will appear black to us. That's because our brains interpret black as not being able to, kind of recognize it. So I'm sitting in a black chair right now, and my mind says, that's not any frequency that I recognize, so I interpret that as black, because the only frequencies I recognize, if you notice, is this spectrum down here, the red, orange, green, blue, purple-ish. So, if we looked at an object that's giving off radio waves, it would appear black. If I looked at an object that gave off microwaves, it appears black. Infrared starts to get, as you might imagine, infrared is red. So we can see a little bit of infrared, but not really. And if it does, it appears red. Actually, stars stars work on this whole spectrum, but there are some really, there are some stars that just illuminate in the infrared. And same thing, visible, as you can see here, and then ultraviolet. We just barely make that spectrum. But notice that when we see ultraviolet, it kind of changes what we see, like black light, fluorescent kind of colors, and then vice versa. So I hope you noticed that, first of all, black represents what we can't see, or what we can't interpret. But I hope you noticed that, a couple colors are missing from this spectrum. First of all, notice that there's no white, right? But clearly, even on the screen, we see that the background is white. So what is white? And notice that actually magenta is missing too. That nice pretty calculator color. Actually, I have it right here. Notice that you don't see pink here. Pink doesn't really exist, right? And I'll get to why in a second, but these are some corresponding wavelengths to colors. Just for fun fact, you don't need to know these, but notice that a bigger wavelength is red and the smaller wavelength is blue. In fact, when I look at stars, when I do my astronomy research, I can tell which one has higher energy just by looking at the color. If I see blue stars, they're going to have higher energy than my red stars. So it's a pretty useful technique. So let's talk a little bit about why we don't see some of these colors. In fact, I'm going to skip that video for a second and talk about it. Now, what we see as white is our brains interpreting all colors at once. So white doesn't actually exist. Crazy, right? What it is putting three lights together. So imagine if I take a stage light. So it has to be a flashlight. It can't be crayons because that's a different mechanism. But if I took a stage light and had green, red, and blue and shined them all together, the three of them will combine as white. Now, you're probably saying that's not true, or you don't believe me, but trust me, it does work, and it's pretty crazy that it does. Now, like I said, this is light, not crayons. And notice that, you've been taught all your life that if you mix, for example, if I mix red and green with crayons, you would be like, I do not get yellow. I get some sort of brown color. Now, you're right, but when we mix crayons, we are actually doing what is called subtraction, so the absorption, versus addition. So this is called color addition and color subtraction. So what you learned in elementary school is that if you did green and yellow, when you mix blue, I'm trying to think of some colors, yellow and green, or yellow and blue, you make green. So you know that, you learned that from colors. But actually, to make the purest green, you can't use any blue, you have to use cyan. And then same thing, red and blue make purple, but the pure red and pure blue make magenta. In fact, if you ever notice that your printer ink actually has yellow, cyan, and magenta, not red, green, and blue. This is how you can make any of the colors. And then notice if you take those three colors and mix them together, you do make black. So, in essence, when you use pigments, you do absorption of colors, and when you do stage lights, you do additive colors. And white is our interpretation of all the light colors. So what happens is we have cones in our eyes, and they're all being active at once. And then black is when the cones do not understand what we're seeing. It doesn't register that detection. So that's what black light is. Now let's talk a little bit about magenta. In fact, this just makes a really good video about it. So let's go ahead and watch it really quickly. After this ad, of course.
When was the last time something was so beautiful?
We've all been told that the colors of the rainbow correspond to different wavelengths of visible light. Red, orange, yellow, green, blue, and violet. Where's pink in that list? It's not there. There's simply no pink light. So where does pink come from? It turns out that pink, or magenta, fuchsia, or whatever you want to call it, is actually a mix of red and blue light. Light from both ends of the rainbow that our brains see as one single color. If you try to roll up the rainbow to make a color wheel, there'll be a gap between red and violet. That's where all of the rest of the light in the universe is supposed to go. Radio waves, microwaves, infrared, ultraviolet, X-rays, gamma rays, and so on. But since we can't see any of those wavelengths, we replace all that hidden grandeur with pink. And speaking in terms of light, pink should probably be called minus green, because pink is just the leftovers of white light when you take out the green.
Okay, so as you notice, it was a really quick video, but ultimately what happens is magenta is our brain's interpretation of two colors at once. So that is what we see here. So our brain sees red reflective light, so the red light's coming out, and blue is coming out. And those two together combine to make pink. Now they were saying minus green, so what's happening is this pigment right now is absorbing all green light, so we're missing that. So our cones in our eyes do not pick up the green, so they add red and blue, which make pink like this. Crazy, right? So that's how colors work for the most part. Now I can go into a huge color theory lesson, but I'm just going to mention that for now and kind of head off on that. So this is why, by the way, when you take white light, so like from the sunlight, and you put it into a prism, you see all the colors. So that's one piece of evidence showing you that white light is all colors. And what happens with this is, and we'll learn about this with Snell's law and refraction of light, is that when the light comes in, we see the separation of colors because what's happened is the angle of the light changes the speed at which the light goes through, and then because of that we can select out our wavelengths. a few more things about light, some properties. First of all, since all light is made by a moving charge, the speed of light remains constant with any part of the spectrum. So all waves, radio, microwave, infrared, visible, all of them have the same speed. In fact, because they have the same speed, we use the constant 3.8 times 10 to the 8th meters per second and use the letter C to represent that. Now, when you look this up and you look on other websites, you'll find that, that there might be 2.998 times 10 to the 8th, which is more accurate, but for our class, for our purposes, we'll just leave it as 3 times 10 to the 8th meters per second. It'll just be easier that way. So anytime you use the word C, this is the constant that you'll use, so make sure you put this on your equation sheets. So regardless, so radio waves travel the same speed as light waves, which is kind of weird because they're oscillating differently. But remember, it's the propagation that we're talking about, not their oscillation. And of course, this is the speed for a vacuum. So we're going to actually put light into things like glass, which is going to slow it down. So this is the fastest that it can go. And even when it goes into glass, it technically doesn't slow down, but we'll talk about that a little later. Since this is a wave, we can use the wave equation to model the speed. But since C is constant, the only things that you really need to know in terms of solving problems is the frequency or wavelength. So C is the velocity. And by the way, it's not given in problems that you're going to see in your homework. It's going to say, what's the frequency of a radio wave that has a wavelength of 1 meter? And that's it. So just know that this is implied that you're going to use this equation to solve for it. Now, F is in frequency and M is in, wavelength is in meters. But as always, because these waves can be really big or really tiny, and the frequency can be really small and really large, they're going to put that in different units. So make sure you convert into hertz meters because we want to use this constant, which is in meters and seconds. So if you don't have it, it won't work. In fact, you could look at these problems, and if you notice, for the most part, that these are in very large units or small units. So yellow light has a frequency of 5.81 nanometers. What is its frequency? I'll just do this one oh so quickly just to show you it, but it's actually pretty straightforward. I don't even think you need me to do this, but as a, let's see if I get it going really quick. I'm going to do this second question right here. So yellow light has that frequency. Wavelength, what's the frequency? So for number 2, C is equal to F this. So C is 3.0 times 10 to the 8th meters per second equals frequency is what we're solving for. But we need the wavelength, but it's in nanometers, okay? So down here or over here. So 581 nanometers. So in 1 nanometer, there's 1 times 10 to the negative 9th meters. So let's go ahead and just do that conversion really quickly. 581 times 1 e to the negative 9th, which gives you 5.81 times 10 to the negative 7th meters. And that will go here. So frequency will be 3.0 times e to the 8th divided by our wavelength. And there you have it. 5.16 times 10 excuse me, 10 to the 14 hertz. Boom. So there you have it. It's a pretty straightforward calculation, so like I said, I'm pretty confident you could figure that out. But these are some of the sample questions that you might see using the wave equation. Now, remember on your exam, you're going to see all sorts of other things that involve waves. So your keywords are the type of wave, like radio wave, light wave, infrared. Anytime you see that, you have to use the constant C and the wave equation to solve it. So just a note on that. In case you forgot your metric units, here they are. You may put this on your equation sheet. Remember, I don't mind if you have these kind of things on there. So I'm just going to conclude the lesson with what light can do. So first of all, light is just a wiggling electron, and it's part of the spectrum, and in fact it's a specific wiggle of that electron. But actually, turns out that light can be modeled a few different ways. And right now in this class we've been talking about waves. So we're actually going to do the wave model of light, and we're going to continue on that journey. And the wave model of light will go into what we're going to study next, which is called optics. But the other wave model has to do with particles, which is photons. I'll introduce what photons are and why we use particle as a way to model waves, because it's really weird to think of waves, light as little balls, but it can actually be modeled both ways. And because of this, wave has a duality nature, which is wave-particle duality. It means it can exist as both depending on how you measure it, which hopefully doesn't sit well with you because it's a weird thing to think about. How can something be a wave and a particle? Einstein was actually pretty confused with this too, but of course he was one of the first people to discover the particle nature of waves. But anyway, we're going to continue our lesson on light with the wave optics, and we'll learn about lenses and mirrors. And then we'll do in the last part of our class will be on photons, the particle nature of light. What can light do? Well, it can do lots of things. So, first of all, light can bounce off materials called reflection. So a light wave can come in, and depending on the material property, the wave can bounce right back off, called reflection. Light can go through materials, called transmission. We kind of talked about transmission, so through medium 1 and medium 2 like this. So a good example of this is windows. Windows can transmit light from one side to another. Light can get absorbed and stay in a material. So, for example, water on pavement, we'll talk about that. But that's another thing that light can do. Light can do more things. If my slides will go. There we go. Light can do this thing called diffraction. So once it goes into a opening, it could spread out. So for example, although I'm talking about light, I'm actually going to use sound, which is a wave property as well. Sound can go around corners, so if you're talking and there's a doorway, someone outside the doorway can hear you, instead of the wave just kind of being cut off. That's called diffraction. Light can do that, sound can do that. By the way, sound can do all these things because it's a wave. Refraction is bending of the light because it goes into a different medium. So the best example is the human eye, so we'll talk about that. And lastly, light can scatter, so it can hit an object and then bounce off in all different directions and spread out. And quite technically, that's why the sky is blue. Light comes in from the sun, and it hits the atmosphere, and when the light hits the particles of the atmosphere, it scatters off of them, and the effect of that is that blue color. So, and the degree of scattering, of course, depends on the angle which the light comes in. So that's why when the sun goes down, you're changing the angle of light, which is why it's red. So you see a red horizon. But when the light is directly into the atmosphere, like at noon, on a nice clear day, you get blue. In fact, you get blue, 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 blue until you reach a certain angle and becomes orange and red. So that's why you see different colors in the sky. It's a scattering effect. So, in conclusion, The next couple of lessons from now is going to talk about some of these facts. In fact, we're going to talk about mirrors first with reflection. Then we're going to talk about lenses with refraction. And then the following lesson we'll talk about diffraction. We won't really go into scattering. We'll talk about transmission, and we won't really get into absorption. But these are all the things that light can do. So there's many things that we can learn about light and how all the different type of matter and materials affect its properties. So that concludes this video on the electromagnetic spectrum. Actually, I will summarize really quickly. So remember that light is made by just oscillating charges. The rate at which you oscillate it changes the name, so from radio to microwave and all that. Since this is what's making the wave, it doesn't need a medium, and it has a constant speed. We could find out its properties if we know the frequency or wavelength. And light has many different things that it can do, and it has two types of models, such as the wave model and the particle model. Now it concludes our lesson on electromagnetic waves.